Hi, everyone, and welcome back to Psych 3510. In this lecture, we're going to be introducing and learning about a, a new statistic that is kind of related to correlations, but not exactly the same as a correlation, as we'll find out. It sort of builds on the idea of a correlation, and that statistic is called linear regression. Some of this is going to look a little bit familiar from correlation. We're still going to be looking at scatter plots. We're going to be, this time, explicitly mathematically defining our line of best fit, because as we're going to see, that line of best fit, if we can mathematically define it, is going to allow us to predict maybe our outcome from our predictor variable. Whereas in a correlation, we were just interested in the relationship between two variables. In regression, we want to be predicting an outcome from another variable. So things are going to maybe look a little similar, but conceptually, there's some differences underneath a linear regression from a correlation. So what do we want to get out of this lecture? We want to understand linear regression with a single predictor. As we will see in a later lecture, we can add predictors and have 2 or 3 or 4 predictors. That's called a multiple regression or multivariate regression. We want to understand how we judge what we call the fit of a regression model. Basically, when we say fit, we're what we mean is how good of a model are we constructing given our data, or maybe you can think about it in terms of we want to predict an outcome measurement. How good are we at predicting, right? How accurate will we be at prediction? This requires a few different types of statistics. We'll discuss them in turn. We can see them here. Some sums of squares, this thing called an F, and then an R squared. And then lastly, we're going to work on interpreting these linear regression models. And then, as I said later, we're going to take the next step of adding multiple predictor variables in a multiple regression. So, as I said, regression is a way of predicting the value of one variable from another variable. In this case, you have one value that is your predictor, right? The thing that's doing the predicting, and another value that is your outcome of interest, right? So in a sense, we have an independent variable and a dependent variable, even though a regression is a correlational statistic in the sense that we're not manipulating anything in the real world. We're not putting people into groups. We're not manipulating a true independent variable for an experiment. Regressions are non-experimental. They are quote unquote correlational in nature, because we are simply assessing already occurring behavior in the world. We're just measuring things. And then with those measurements, we're trying to predict. This is a linear regression, so we're going to end up creating a straight line, a line of best fit, that will model the relationship between our two variables, the predictive ability. And so one of the things that we want to really keep in mind is that regressions are used to predict, correlations are used to associate two variables. So if you're interested in simply the relationship between two variables, you want a correlation. If you're trying to use your current data to predict something about the future, then we want to be working in a regression. So the line of best fit. You can see in yellow an algebraic formula for a line. This is basically just your y equals mx plus b, where y is our outcome, all right, our variable of outcome interest. B is our intercept of our model line when y equals 0, plus our regression coefficient, which is essentially the slope of our line, times x, which is the given value of our predictor, plus e, which is error, which is going to remain undefined, unspecified. It's in the model, or it's in the formula. so that we can sort of remind ourselves that there's always unexplainable error out there that we cannot fully capture. But this is not actually going to have a quantity. This is when we really use this to make predictions, we're just going to pretend like this error doesn't exist because we can't define or quantify the error, right? Think of this as, you can't know what you don't know, right? If there's error out there in the data, it's coming from 1,000 possible places. We can't quantify or define it. All that we can define is our intercept, the slope of our line, and then our value of our predictor variable x. Okay, so let's think about this in terms of an example that we'll see come back throughout this lecture. Let's say that you're a record company executive and you want to be able to predict how advertising dollars for an artist impacts their record sales, right? As the record company, you are spending lots of money promoting the record, promoting the artist, right? Plugging money into advertising. And so you want to be able to know, how does advertising predict record sales so that you can make adjustments to the amount of money you spend on an artist. So if we take this example and we plug it into our formula for a regression line, a regression equation, y is our outcome. That's the thing we're interested in predicting, which is record sales. Our b sub o is the intercept of our line. This will essentially become the number of records sold when we spend nothing on advertising, right? When our x axis variable, which is our predictor, when our x-axis variable equals 0, how many records are sold? So if we spend nothing on advertising, how many records are sold? That's our intercept. B sub 1 is our what we call our regression coefficient. This defines the relationship between advertising dollars and sales, right? This is the thing that is going to tell us, for every dollar in advertising, how many record sales do I get back in that, right? Or for every $1,000 in advertising, how many record sales do I get back? This is the slope of our line. X is the predictor value that we input. So the amount of money spent on any given artist. So once we use our current data to construct this line, we can play with X and we can say, okay, if I spend $100,000 on advertising, how many records do we predict this artist will sell? If I spend $200,000, how many records will this artist sell, right? X is our input of our predictor, right? So this will change based on what our predictor is, right? How much money we spend on any given artist. And of course, we have E, our unspecified error. That's not going to factor into our equation. So you can see all the bits and pieces of this formula map onto our example. Y is our outcome, record sales. B sub O is our intercept, how many records are sold if we spend $0 on advertising. B sub 1 is the slope of our line. It's the relationship between advertising dollars and record sales. And then X is the amount of money we choose to spend on any given artist. Now, one important thing to point out is that to construct this equation, we need data from the past. So what a regression does is it takes data that you already have, and it says, let's use this data to build a predictive model for the future. So before we can even try to construct this equation, we need to have a backlog of data on these variables, right? So the record company is going to go into its accounting department or whatever, and it's going to say, can you give me from the last 100 records that we've released, how many records were sold and how much we spent on advertising? And then we can use our data from the past to construct a predictive model that we can theoretically and hypothetically apply to future sales and advertising dollars. So the whole point of a regression is to use your past to predict your future. And this line is the thing that we come up with as our equation for prediction. So a couple points about that line as well. We've had a couple terms, intercept as well as slope, or you could also call them gradients. So in a regression equation, you will see, in a regression figure, you will see the predictor variable on the x-axis. So in our example, this would be advertising dollars, which will predict our y-axis variable, which is our outcome of interest, which in this case is records sold. Now, when we say intercept, intercept is the point on the y-axis where the line meets the y-axis, meaning if our predictor value is 0, if we spent $0 on advertising, how many records would be sold, right? This number of records. We can see here that these two regression lines have the same intercept, but they have different gradients. They have different slopes. This green line has a negative slope. This red line has a positive slope. So if our regression equation using our data from the past yielded the red line, it tells us that as our predictor increases, right, as we spend more money on advertising, we should expect more and more and more album sales, right? And then we can fit any point on that line, any point on our predictor to that line, and then we can ask ourselves how many albums we should sell over here on the y-axis. Now, this wouldn't make a whole lot of sense in our example, but if our regression equation returned our green line, then what this tells us is the more money we spend on advertising, the fewer albums we sell, right? It's a negative relationship. So that seems a little similar to correlations. So hopefully maybe that helps us understand, but keep in mind, we're no longer just assessing an association. We're actively using this line to try and predict things about the future. Over here on the right, we can see 3 regression lines that have different intercepts, but the same slope, the same gradient. So just sort of hammering home our distinction there between slopes or gradients and intercepts. So how do we calculate where this line goes, right? It's called the method of least squares. Basically, you take all of your data points. These are our blue dots here. And we calculate, and the computer is going to do this for us. We're not going to actually calculate it by hand. The computer calculates the line that we can draw amongst these points, which reduces the cumulative distance of our points to the line itself, right? So the points sort of in this quadrant are above the line. The points in this quadrant are below the line. And we want the line that gives us the least amount of difference cumulatively of all of our data points added together to that line. So here we can see this data point is pretty far away from the line, but these data points are really close to the line, right? So they conform a little bit better to our prediction, which is something that is important to realize, right? These blue dots are actual real data, right? They are real advertising budgets for real albums sold for a particular artist, right? These blue dots represent things that actually happened in the world. The green line, which is our regression equation, is not actually something that exists in the real world. It's our model of the relationship between advertising budget and album sales. It's using our previous data to say, if we had to come up with a way to predict this relationship in the future, what is our best prediction? And that's the slope of this green line. And then we could take this green line and we could plug in any value along our x-axis, which is our predictor, advertising budget. And this is in thousands of, that's pounds, not dollars for this example. So we could say if I spent 2,000 pounds, so that's, quick math, what is that, like $2 million or 2 million pounds? If we spent 2 million pounds on advertising, we should expect 300, and that looks like about 60,000 album sales. Right? And so once we have the line, our data points have done their job, right? We can sort of ignore the real data in a sense, because the purpose of these data is to give me this line so that I can take this line and use it in the future. But it's important that we note that the data points are real and are from the past. The line is an approximation of those data points that we can use for prediction in the future. Okay, that's basically what I just said. But one thing that we have to consider is that just because the computer gave us this line doesn't make the line good or useful, right? We could use data from the past to create a predictive tool, and nothing says that that tool has to be a good tool, right? We could have screwed something up, or the data might be inconsistent, or something might change in the future to completely revolutionize, for example, the record industry, right? So maybe we're using data from the 1980s and the 1990s when the music industry was dominated by record labels, right? And that's all there was. Those data would not be very good predictors of album sales today in a completely different music industry, where things are changing. You can get famous on YouTube, and in fact, YouTube views now count, towards like going platinum and things like that, or SoundCloud, right? It's completely revolutionized the record industry. So just because we can take old data and create a model doesn't necessitate that that model is any good. It doesn't necessitate that that model is helpful. So what we need is a way to statistically validate whether we have a good model or a poor model. And so that's what we're going to learn about next. How do we know if we have a good model or a poor model? Again, what are the reasons that we might have a poor model? Where we could be measuring things poorly. We could track album sales by just asking people if they bought an album rather than looking at iTunes sales. Maybe our accounting department doesn't do a very good job of keeping accurate numbers on our advertising dollars, right? So we're starting out with bad data. Or we could be choosing the wrong predictor variables, right? So we're interested in album sales. Maybe advertising dollars doesn't have a lot to do with that anymore, right? Maybe it's more about popularity of the artist, or social media presence, or genre of the music, right? Just because we chose advertising dollars as a predictor doesn't necessarily make it a good predictor. There might be other better predictors out there. And so this is one of the reasons why, as we'll see in our next section, why we have multiple regression, where I could include advertising dollars, artist popularity, social media presence, and maybe something about the genre of the music, all into a single model that will create a single line, which would presumably be a better predictor because it's using more information to make that prediction. But again, that's going to be for later. Okay. Caveat before we get started with a little bit of the conceptual math here. You will not have to do any of these calculations. What you'll be presented with is computer output after a computer has done the calculations for you, such that you can interpret the calculations. You don't have to know how to do any of this mathematically, but we're just going to talk about it very quickly conceptually. How does the computer, how do our statistical programs make this assessment about the fit of the model or the goodness of the model? It uses three calculations that we can think of as a sum of squares. So first, our total sum of squares is the distance of all of our data points to the average score on our outcome on our y-axis. Let's say this red line represents the average score on our outcome, and each of these dots represents a real data point, right, with a predictor x and an outcome score on y. So the computer then draws this blue line of best fit, and we can conceptualize the distance of the line from the data points as error, right? This is the amount of error in our model, because the line cannot intersect all of these data points, right? It would not be a line if it did that. It has to approximate the data points, and when we approximate the data points, there's drift, right? There's error. The data points are not perfectly on the line, and so we can conceptualize the error, the variability in our predictor as the distance from the data points. This will be minimized by the line, but it can't be infinitely minimized, right? Some lines will produce more error than others, depending on what the data look like. And then lastly, we can have a sum of squares value that is the distance of our predictor line, our regression line, our blue line here, the distance of that blue line from the mean of y. So sum of squares total. Let's put it in into our example. Each black dot has a score on the x-axis, which is advertising dollars, and a score on the y-axis, which is albums sold. Each dot represents an album. And so we can think about the total variability, the sum of squares total, as being how far do each of these points drift from the mean of our outcome. Our error, or our sum of squares residual, we actually call these distances between the line of best fit and our data residuals. Think of them as error. This is the variability we observe between the data and the regression line. A low sum of squares residual means that the line is really, really good. It's really, really tight to the data. A high residual sum of squares means that we're not looking at such great predictive ability. For whatever reason, our chosen variable is not an amazing predictor. So we want these residuals cumulatively to be as small as possible. And lastly, our sum of squares M, or model. This is the difference between our regression line and the mean of our outcome. So what's happening here is that we want the blue line that we've drawn, that new predictive equation, we want this blue line to predict values better than just the average of y. So we want better predictive ability than just if we were to use the average, right? So for example, if I asked you, can we predict album sales using advertising dollars? And if the average of album sales is 100,000 albums, right? Our outcome is 100,000. If I just guessed 100,000 every time, because that's the average, and I did better than your regression equation, then your regression equation is useless, right? Your predictor is useless, because just guessing the average is better than your attempt at prediction using another variable, which is advertising dollars. So I'll say that again. The whole point of this is that we can bring in a second variable, advertising dollars, and we can improve our predictive ability of album sales, our outcome. So if someone asks me, hey, Mr. Record Company Executive, how many albums do you think Ariana Grande will sell on her next album? And if I just guessed the average of all album sales, 100,000 albums, and just guessing the average did better than your predictive equation, then what's the point of your predictive equation? It's not adding anything of value to our ability to predict. So, SS model assesses the degree to which our regression equation line does better than simply just guessing the average of our outcome. You can take them and produce a mean squared by dividing by degrees of freedom. We won't, again, you don't have to do that. Don't worry about those calculations. Just know that we're going to take these sums of squares and we're going to produce something called an F value. An F value is like a t or a chi-square. It's going to allow us to assess the statistical significance of our model. That's all you need to know. The F value is going to allow us to test the statistical significance of our model, and we mathematically derive that F value from these sums of squares that we've seen. You don't need to know how to do that calculation, just know that it happens. The other important statistical outcome, which again, you do not have to calculate, you just have to be able to interpret, is called R squared. R squared is the proportion of variance accounted for by the regression model. So if R squared is 0.35, and let's keep with our example of advertising dollars and album sales. If R squared is 0.35, what that means is that advertising budget accounts for 35% of the variability in album sales, which is probably pretty good, right? Because there's, like we discussed earlier, there's a lot of things that go into who sells how many albums: popularity, social media presence, genre of music, right? All that kind of stuff. And so if we can account for 35% of that variability with just a single variable, we're doing pretty good. So R squared tells us the percentage of the variance in our outcome that is accounted for by our predictor. Now, R squared has an interesting property because it's related to correlation. If we take away this squared, which we would do by taking the square root of R squared, we would end up with R, which is our correlation coefficient. And that's calculated using the sum of squares as well. Again, you don't have to know how to do that. Okay, so let's actually play through this example using data as a record company executive predicting album sales in the future from advertising, hypothetical advertising dollars. So we go back to our accountants at the record company and we have them pull the last 200 album releases. We are predicting sales. So back in the day when we actually used to have physical CDs and downloads in the week after release of the album, and the amount of money we spend in thousands of pounds on advertising. That's our predictor. And let's say that this is what our data look like. Right? Each dot is an album. We can follow each dot down to the x-axis, and it tells us how much money we spent on advertising. So, for example, this album right here that I'm sort of circling with my laser pointer, we spent, if we track down on the x-axis, right, just over 500,000 pounds on advertising. Right. Notice that this x-axis is advertising budget in thousands of pounds. So that doesn't actually, this 500 doesn't mean we spent $500 or pounds. It means we spent 500,000 pounds. And so for just over 500,000 pounds, this album sold 300,000 copies. It's in thousands. Again, just to sort of make these numbers easier to deal with. So we could take each data point and we could track exactly the advertising budget and the album sales. The computer draws this line for us, and it says, if we sort of average all of these data points together, what we get is this line. And we're going to use this line to predict the future. right? These are albums that have already happened. They've already been released. They've already been sold. They are what they are. They are real, right? These albums actually occurred in the real world. This line is an approximation of our predictive ability of advertising budget to album sales. And so we can take this line and ask questions about the future. So the upcoming album next spring, right? If we spent 200 or if we spent 2 million pounds, what should we expect in return? And so thus, as a business, right, a record company, we can use this information to adjust our advertising budget accordingly in an effort to be as profitable as possible. Oh, sorry, that's getting cut off here at the top. Don't know why that's happening. I'll see if that's happening on the static PowerPoints and try and go back and fix that if I can. So the first thing that we end up with, or I'm sorry, the second thing that we end up with from the computer, the first thing is the line of best fit. The second thing is a summary of our model. This is where we get the correlation between our two variables. And this is where we get the percentage of the variance, R squared. Don't worry about these two things over here, the adjusted R squared and standard error of the estimate. They need not concern you right now. We just need to focus on these two values, R and R squared. So, advertising budget and sales has a pretty high correlation, right? 0.578. That's something that we would call a large correlation, a strong positive correlation. So the more money we put in advertising budget, the more album sales we get. R squared tells us that advertising budget predicts 33.5, right? We want to move this twice because it's a percentage. 33.5% of the variance in our outcome, which is album sales. So if you said, what makes one album sell more or less than another album? I can explain 33.5% of that difference using advertising budget. Other variables that I have not included in the model are responsible for the other, what would that be, 66.5% of the variance. So advertising budget explains about a third of the variability in album sales. But 2/3 of the variability is still out there somewhere in the world from variables that we didn't include. Now, what the computer is also going to give us is an F value with an ANOVA table. That's a new word. It stands for analysis of variance. This tells us if that prediction is statistically significant. So the model summary tells us how much prediction we can do, right? What percentage of the variance are we accounting for? Right? What sort of weight of prediction do we have here? And the ANOVA table tells us, is that a statistically significant amount of predictive ability? Here's our F value. We sort of talked about that this is derived from our sum of squares. Here we can see that the computer calculates all those sums of squares. You don't need to know how to calculate them, don't worry. Produces an F value, which is our test statistic for significance here. And it produces a significance value. So if you think back to T's and chi-squares and R's correlations, we had to have a table that told us a cutoff point so that we could make our decision about statistical significance. Well, if you're doing something in a computer, you don't actually need that table because the computer can do it for you. You really only need the table when you're doing it by hand. And you really only do it by hand when you're learning it in 3510 and 3530. If you ever have to do any of this in the real world, you won't do it by hand. You won't need a table. You're going to do it with a computer, and the computer does the significance calculation for you. Now, This significance value is a little sort of inversely counterintuitive, meaning this is not a critical value like on the table. What this does is it already does all that logic for you, right? The computer has its own critical value that it's using that you can't see behind the curtain. And so what it's doing is it's giving you a number to represent a comparison to your alpha for statistical significance. If significance value is less than alpha, then the effect is significant. I'll say that again. If our significance value is lower than alpha, which would be 0.05 or 0.01, then the effect is significant. So we can think about what does alpha equals 0.05 mean. Alpha equals 0.05 is saying we want to be in the 5% most extreme result in order to be significant. Right? The 5% most extreme. Because we're using a calculator here, it can tell you the exact place on the curve where you fall. And in this case, we are very extreme. We are the 0.000 most extreme place on the curve. The computer program cuts this off at 3 decimal points. You can imagine that this number sort of goes on to the right, and somewhere down there, it's 0.00000, maybe 37, right? There's digits down there somewhere. But it's telling you exactly where on the curve you fall. So if your significance value is 0.25, what that's telling you is you're in the 25th percent most extreme, which is not what we want, right? We want either the 5 or the 1% most extreme. So if your significance value is larger than alpha, it's telling you you're not extreme enough. If your significance value is smaller than alpha, it's telling you you are extreme enough. You are in the 0.1% or 0.00001%, right? You're super extreme, right? So here, a small significance value means we are extreme. A large significance value above our alpha means we are not extreme. So don't get that confused with critical values. We're not using a critical value table here because we have the computer to do it for us. And you'll learn how to use this computer program most likely in 3530, but we're not getting into it here in 3510. The next thing you're going to get is called the model of coefficients or parameters. This is where we derive the exact nature of the slope and intercept of our regression line. Don't worry about all this stuff over here to the right. What you need to worry about are what are called our unstandardized beta coefficients. Unstandardized beta coefficients. The line that says constant is our y-intercept. So what this tells us is that we would sell 134,000 albums if we had 0 advertising budget. That's what the line predicts. Might not be realistic, but again, the line is not perfect, right? So this is our y-intercept, 134.14. And this 0.096 is the slope of our regression line, or in other words, the change in outcome with 1 unit change of our predictor. So for every unit increase in our budget, we get this many album sales. And remember, these are all in thousands. So for every 1 unit of advertising budget means 1,000 pounds. So for every 1,000 pounds, we get 0.096 thousand additional album sales, which if we do the math is 96 album sales. So what we want to be able to do is identify these unstandardized beta coefficients, take them and plug them into our predictive regression equation like so. So y is our predicted number of album sales. 134.14 was our constant, which is our y-intercept, BO, plus the slope of our line, 0.096, which is the predictability of advertising budget, essentially, times X, which is whatever advertising budget we want to put into our next album, right? X is going to change based on our prerogative as a business, right? This is the predictability. X hasn't happened yet, right? X is the hypothetical advertising budget of the future albums. So remember, these numbers 134 and 0.096 are derived using the past, albums that have already been sold. X are albums that don't exist yet, right? They are future albums that we have not released, that have not been sold. And we can plug in the advertising budget, that's what X represents. And then we can just do the algebra and we get a Y, which will tell us how many albums we can expect to sell. So, if I wanted to, let's focus on this lower one here. If I wanted to say that for our next upcoming album, we're going to have an advertising budget of 100, remember 100,000, it's in thousands, 100,000 pounds of an advertising budget. I just do the math, 100 times 0.096 plus 134.14 yields 143,000 album sales. 143, technically 0.74 thousand album sales. So if we moved this decimal point 3 times, right, we'd have 143,740 album sales. So this 100, right, remember, is the advertising budget of an album that doesn't exist yet, but we're using this formula that we've created to say, if we spent 100,000 pounds, how many album sales can we expect? So we can do that for any amount, right? So instead of 100,000, what if we bumped up the advertising budget to 250,000? So we just do the math again, and instead of 100, we put 250, and we get 158,000 album sales, or 140,000 album sales. And so as a corporation, we can sort of do the cost benefit and the math here and decide, is it worth it to spend 250,000, or should we be spending less, right? Are we getting a return for our money in these album sales or not? So I want you to take a minute and work through this practice problem. So press pause, and then once you've tried to work through this practice problem and you'll see the answers come up, I'm gonna walk through it and explain it as well. So press pause, take each slide one at a time, do what the slide asks of you, and see if you're getting the answers right, and then come back and press play for my explanation. All right, hopefully you've done that. So here we have an example. Maybe we own a car dealership, and we want to try and predict the amount of money someone will spend on a car. So the price of a car is our outcome. And we want to predict how much money someone will spend on a car based upon their income, which is our predictor. So we collect data from the last 20 people that bought cars, right, in maybe the last month. And we have data on how much money they make, and we have data on the price of the car they bought. We're going to assume alpha equals 0.01 for this example. So just pretend like, we've put all the data into the computer, and we told the computer to run a linear regression, and it produces this ANOVA table for our overall model. We can see that our dependent variable is in fact price of the car, and our predictor is income. So the first question you have to ask yourself, does income significantly predict the price of the car? And the answer is yes. We have an F of 57.737, which is derived from our sums of squares. And the significance value is lower than our alpha of 0.01. So we can say confidently that income is a significant predictor of price of the car. We don't actually even need the scatter plot, nor do we need to see the regression line to make that interpretation. We just need this ANOVA table. So yes, income is a significant predictor of how much someone will spend on a car. The next thing we need to ask ourselves is, what is the line of best fit formula, or what is the formula for the line of best fit? We can see it in general over here in sort of its algebraic form. But we're given this coefficient table, our model parameters of our constant, which is our y-intercept, and then our predictor variable, which is income. Notice this is not income in thousands anymore, or price in thousands. They just are what they are. So we don't have to do that little thousands calculation for this example. So we have our unstandardized beta coefficients. This is our y-intercept, 8,286.786. And this is the slope of our line, 0.564. So we can already tell this is a positive relationship. So obviously, people who make more money spend more money on a car. We can plug these two values into our formula over here to produce this line of best fit formula. We take the constant, and that becomes our y-intercept. We take the slope, that goes here, and then we can now do the work of plugging in anyone's income, and using our last 20 cars sold, we can predict, using their income, how much money they will spend on a new car. Notice that if you make zero money, the model still predicts that you will spend a little over $8,000 on a car. This highlights, just like the advertising budget question did, that oftentimes these models don't have good predictive value at the intercept, right? If you have zero income, you're probably not buying a car, even one for a little over $8,000. So that's a constraint on our model, and is a constraint on most linear regression models. They tend to only do a good job once you've moved beyond zero for your x, right? Once you actually have, for example, income. But anyway, we can take this formula and we can use it to answer these questions. Given the previous example, how much would we predict each of these people? How much would we predict each of these people would spend on a new car? So someone who makes $105,000 a year, we take this formula, we plug in their income, we do this multiplication to get 59,220. We add it to this, our intercept, and we would predict that someone who makes $105,000 a year would spend $67,506.79 on a new car. So someone with a lot of income is going to spend a lot of money on a new car. Let's look at someone with lower income, $34,000 a year. We plug it in for X, we do our math, and we're going to predict that they're only going to spend $27,462.79. So they make less money, and we predict that they will spend less money on a car. And then we can play around, and we can hypothetically put the income of any person into this equation. So someone who makes $71,400 per year will spend, right, plug and chug, do the math, $48,556.39 on a new car. Again, don't forget, this equation is a model that we use to predict the future. This is a statistically significant model, but that doesn't mean that it will be perfectly correct every time, right? This person that makes $71,400 a year might come in and say, I'm trying to be more budget conscious. I'm only going to spend $30,000 on a car, right? Or whatever. Because there's other variables that we don't have in the equation. Income is not the only thing that impacts how much money someone will spend on a car. Maybe whether they're married or not, maybe whether they own a home, maybe their age, right? Someone who makes $71,000 as a 25-year-old might behave very differently from someone who makes $71,000 as a 65-year-old. Right? Those two, age might be an added predictor. So it doesn't mean that they will spend $48,500 on a car. It just means that's the best we can predict given the information we had from the past about income. So in our next section, what we're going to work on is building more complex models by adding multiple predictors. So just as I said with this example, income is not the only thing that we can use to predict. We might want to add age. We might want to add, what are your other monthly expenses? We might want to add the size of your family, might predict how much you spend on a new car. There's a myriad of other variables that we can include in this model that might help us have even better predictive ability. And so that's what we're going to take a look at in our next section with multiple regressions or multivariate regressions. Thanks, everybody. And I will talk to you later.